Good morning, good afternoon, good evening, everybody. Sorry, we had some technical difficulties. Thank you very much for anyone that's still on the line for being patient. Today we have Bob Shaw, who's going to do an overview of border control connectivity solutions. So Bob, I will hand it off to you.
Well, good morning / good evening for everyone involved, and apologize for taking so long to get our technical difficulties ironed out, but we did get them, so that's great. So Susie, next slide, please. So our topic for today is really considerations and planning and building connectivity for border security systems, and discussing all of the things that are required and the challenges that we might face with those, and how we do build those. So next slide. Okay, so from an agenda standpoint, we are going to talk about border security systems, what they do in a relatively simple format. I mean, they can be more complex than we're going to cover today in the time that we have allowed, but certainly there's a number of things involved with what we accomplish with these kinds of systems and where we might apply them. The technology can be applied in lots of different places, and what are the things we need to do. From a requirement standpoint, certainly the challenges we face, or the requirements that our customers have, are that these systems generally, because border areas are generally not always, but generally more rural and less populated, you need rugged equipment. You need things that can last, things that are going to be very, very high temperature, very, very low temperature. Significant amount of corrosion can happen in places like this. So depending on where it is, we need to consider that. We certainly need high throughput, because as everyone knows that in the past, border security systems might have been about tripping an alarm. Is there movement in a place? Things like that. Small amounts of SCADA data might have been used to say, hey, there's somebody near our border. But today, the applications are significantly more complex than that, especially with integration of everything from social media to gunshot sensors to video cameras and radars and lidars. All those things really play a role. So we really have to have enough throughput to be able to get the data where it needs to go. And then the other thing about throughput is that it needs to be a little bit more asymmetric. Generally, all the things I talked about, the data is going from the border back into the network, where people are actually monitoring and looking at what's going on in a network, and then deploying responses to those challenges. And so the data is really asymmetric. And so having a symmetrically built communication system that handles lots of data in both directions is sometimes wasteful, and sometimes this doesn't get the job done for what we have available with us. So we are going to consider those. On the challenges side, we're certainly going to talk about topology and the terrain involved, because there's lots of different things when it comes to terrain on border systems. We talk about RF resiliency and agility. Those are both important aspects to talk about a little bit. And we'll spend a little bit of time on link planning and planning out these things and what tool we use. And of course, for us, that's called LINKPlanner, is how we do all of our RF communications planning. And then lastly, mitigation of security issues. Because if I've got a network, then I've got to have security on that network to make sure that I'm not being infiltrated by the wrong people. And how do we work with that? And then certainly we'll end with questions and answers. So Susie, if you get the next slide. Okay. So what is a border network? Well, border networks, I mean, obviously networks and on the borders of countries or states, municipalities, regions, all those kinds of things. They help keep the country and people safe, both in the U.S. and Canada and North America and all throughout the world. These things exist, and I built them in many countries for many different applications. But at the end of the day, it's keeping people safe. And we can use the same technology in smaller places and in very, very large disparate areas as well. We're providing advanced warning, whether it be at land or at sea. Recently built a network that was really a maritime surveillance network. So it was really all about surveilling the oceans around a country to look for people that have ill intent or bad intent, and making sure that they can't, using high speed boats, go over the horizon, travel along a coastline, and then come straight in. And that applies both for smuggling as well as illegal immigration, terrorism, all those kinds of things. It applies to all of those. So we have to build networks that can handle that kind of provide warning for those kinds of situations. And so we talk about that. We can talk about that from a situational awareness standpoint. What exactly is going on, and are we aware of the situation at all times? You're always going to have never enough resources, always too many problems. So the more data we can get to the right number of people, the better we are at knowing what's going on at any given time. And of course, you have to consider that there's both tactical and fixed in nature. Fixed deployments obviously are where we're building towers or we're using existing vertical height assets, mountaintops, buildings, things like that along the border to create a security network. In addition to that, though, you have to think about what are the things that are always going to be true. And one of those is that bad guys will always look to see where is the easiest way to get across a place. How do I get across this border the easiest way? And if I built these very, very nice, very expensive fixed assets, well, then they're going to go somewhere else. And you can't always build huge border networks very easily, very quickly, especially very quickly. And if we have to respond, it'd be nice to be able to take and respond in a tactical manner and have tactical products that can actually be moved rather quickly and deployed in places where infrastructure may not be easily available or almost impossible to build. So we have to think about those as well. And again, we're regulating trade and enforcing country laws, those kinds of things as well. They're all important there. So next slide, please. So talking about requirements standpoint, again, I want to build networks that have 5 nines or better reliability, if I can do such a thing. I need to have something that's a mil standard 810G ruggedized product. We want to have things that have we'd like to have products that have Amphenol connectors on them or something like that, where I've got rugged cabling, I've got rugged power supplies, rugged lightning arresters, rugged everything, so that I can really deploy this and not have to have RF engineers deploying these things. I can have operator level people deploying and getting it to work properly. That's all important. Throughput, obviously, multi-hundred megabits sometimes to gigabit, depending on where you are in the network. Power is another concept that's really interesting, and that is where I've got low power availability. And the really great thing about mountaintops is that mountaintops are excellent for view. I can see very, very far. I can create very long microwave links. I can get cameras in great places sometimes, things like that. Not a lot of power though. And so you've got to either have solar power or you've got to have propane or wind or some mixture of those. And you think about it, in the United States, we have Alaska. Alaska is a great example. Great mountaintops, lots of views, be able to see and hear very, very far. But at the same time, and in the summertime, we have 2 months of absolute continuous sunshine. So solar power is great. But then 6, 8, 10 months of the year, those same mountaintops are covered in snow, and there's no solar at all. So I've got to have a lot of propane up there. And propane is costly, and helicopter rides to get it up there are costly. So you got to think about those things in advance. And of course, as I talked about before, being asymmetric. And how do I deal with data that's usually up to 90% from remotes downstream into the network? Those are things that we have to kind of figure out as we go. So Susan, next slide. All right, so proven reliability, making things rugged. Obviously we're Cambium networks. We make radios. The PTP 700 is our newest tactical deployable radio, and it's been around for about 3 years now. We actually have only one radio in all that we shipped in 3 years. We only have one radio that's actually failed based on workmanship or materials or software. We've had certainly radios that are hit by shrapnel or dropped off a truck or struck by lightning, but when it comes to the actual radio failures, we only have one PTP 700 failure to date, and we shipped several thousand of them. If you look back at the previous generation, the PTP 500, the 600, the 650 radio series, those guys ran at a mean time between failure of 377 years on a run rate of over 100,000 nodes deployed. And the really interesting fact is that of the PTP 600, which was really our flagship radio for a very long time, we only had 4 failed as DOA, or dead on arrival, coming out of the box, and didn't work in 12 years of total life of that product. When we shipped the original 58600 through the last of the 4, 5, 600s that we shipped a couple of years ago. So 4 out of, thousands and thousands and thousands. It's a pretty good quality from a reliability standpoint. So next slide, please. And of course, the PTP 700, what makes it stay with that same quality? Well, we rate it from minus 40 Celsius up to plus 60 Celsius. And so we test every last one of those radios before they leave our factory floor. So they go into a cold cycle that the internal temperature is minus 40 degrees Celsius for 30 minutes. And then it runs a cold start test and a functional test. And that's got to pass all the tests, all the modulations, all the channel bandwidths, except for full power ranges. Once it gets done with that, we take it out of the freezer. It takes a number of hours before it gets back to ambient temperature. We go back into the oven now, and from the oven standpoint, it gets into the oven. We raise the internal temperature of the radio to plus 60 degrees Celsius for 30 minutes, and we run all those tests again. So we've tested it at its extremes on the cold side and on the hot side, and it's every radio. So the chances of these things not working out of the box are very, very, very low. So that makes for high reliability, and it also gives us a very good manufacturing process that we see something failing, we're able to fix that before it ever hits you as a customer. So next one. Okay, so we have 2 different products to talk about here. We talked about the PTP 700 quite a bit today, but we also have something called the PTP 820. And both of those radios, radio families, have uses. I'll kind of just compare and contrast a little bit in the thought process of how do I get high throughput? Because I've got a reliable radio, I've got a rugged radio, I've got something that's extreme temperature tested, but now what about the throughput? Is it going to do the job? And that's where we look at this. And so the PTP 700 has a 450 megabit per second aggregate capacity, which may do the job for most border networks. And in many cases it does. It's a wideband radio, so it has a significantly wide frequency band. The current product is the 45700, and it runs from 4400 to 5925 megahertz. So that radio can handle the 4 gigahertz NATO band, as well as all the unlicensed bands, the 4.9 public safety band, all of those in between. We're also bringing out something called the 78700, which will be due next year, and that product will be the 7 and 8 gigahertz version of a 700, and it'll support both NTIA and ETSI frequency variants. So again, one nice thing about it is that it's one radio for the entire band. We don't have any sub bands. We don't have to worry about highs and lows. And from a sparing and logistics standpoint, we've got one device across the entire network. One other thing about the 700, of course, is that it does point-to-point or point-to-multipoint. Our point-to-multipoint software add-on is called HCMP, or High Capacity Multipoint. High Capacity Multipoint allows up to 8 remote subscribers, all PTP 700s, talk back to one access point, again, a PTP 700 radio, and I've got some high capacity amongst each of those. Normally we run slightly less than 10% overhead on multipoint, which gives us in the range of 400 megabits per second on an access point, which can be shared amongst the remote subscribers. And they can be asymmetric themselves. There's a lot of actually very cool options that we won't talk about today, but our HCMP implementation has both a standard mode and an expert mode, and it actually allows for lots of flexibility when it comes to building networks. So Another thing that 700 has is, of course, jamming and interference mitigation. Because we have a dynamic spectrum optimization, which adds frequency agility, we can actually do, we can have the entire band wide open, and so the radio can choose best frequency availability at each end of the link. So I can have an asymmetric configuration on frequency, or I can be as locked down as you want to have it based on spectrum management and frequency assignment. And of course, it does include the full-time spectrum analyzer, which nobody else in the industry provides today. And it's across the entire band. So that's very, very cool. And of course, from a security standpoint, we'll get into security a little bit later on. But FIPS 140 and over-the-air rekeying using TLS rekeying is actually very cool. So we'll talk more about that. The 820. So the 820 is, of course, a radio that is a full duplex traditional microwave. It does not do near and non-line of sight the way the 700 can. So you really have to have clear line of sight. It is for fixed applications only. It can do very high capacity though. I can get, depending on the configurations and the amount of frequency bandwidth available, I can get from 250 megabits full duplex up to 2 gigabits full duplex in the right configuration. So more of a backbone radio than an edge radio. And it allows us to have aggregation of significant amounts of data that can get back to my network. It's higher frequency, so there's rain fade associated with it, depending on the frequency, especially over 10 gigahertz. We really have to consider that when it comes to our reliability. But we have both NTIA for U.S. Government, as well as FCC frequencies for U.S. commercial, and we have rest of world. Basically, ETSI is rest of world, and we have ETSI frequencies from 6 to 38 gigahertz as well. So lots of opportunities from a standpoint of using that product in the backbone throughout the world, depending on the region and the frequency availability. And of course, that radio has a number of things it can do, which are really pretty cool. You can have 1+0, 1+1 standby. We can do 2+0 and 2+0 XPIC, so I can double up throughput. I can do 2+2, so I can have high capacity and high redundancy. And I can do things like a 1+0 east-west. Kind of interesting concept that I've got basically one system as a repeater site, one looking east, one looking west, north, south, etc. And 4+0 configurations as well. So we can do a lot of very, very high throughput in the right application. They'll require some planning, but certainly can be done. So from a throughput standpoint, you've got really two, from Cambium Networks, we have really two options. One is the 700, and then one is the 820. The 700 can really work in vastly everywhere, but there are going to be times when you need additional throughput. The 820 can fit that need. So Susie, next one, please. So just to give you an example here about power draw. So this is an example of a site in Alaska that in the summertime has 2 months of clear weather, and pretty much solar is no problem for 2 months of the year, and not a problem. But if you look at the left-hand picture, you'll see some things on the ground next to the tower. That's actually the shelter and then the propane tanks. And they normally have to keep 2.5 years of propane on site, because getting helicopters up there with weather, even in the summer, can be difficult, and you may not be able to fit it in depending on the storm season. So they keep 2.5 years of propane up there. We found that with the predecessor product that had been up there and the original system, that we had about 7 times less power draw on the PTP 700 than the predecessor system. So they were drawing over 300 watts continuously. We came in with a radio that actually did 35 watts of continuous draw, and they were actually able to pay for the radio system, the PTP 700 radio link, on these locations in 1 year, because the propane costs were so high and the helicopter costs are so high. So they were able to drop their power requirements significantly, and drop the draw, of course, and that's less stress on the entire system, allowed them to pay for the system, literally the radio system, in 1 year. So it really is a concept we have to deal with. And in the tactical space, you've got to deal with generators, and you've got to deal with fuel. All those things are common. So power is an important thing. And yeah, there's products out there that are going to be less draw than a PTP 700. Probably not going to find the same capabilities though for the amount of power draw that we have. So Next slide, please. Okay, so uplink and downlink being asymmetric. When we think about video communications, any video camera, the most wonderful cameras in the world will put out some great video, and I might be able to see an awful lot of things, but I don't really need to talk to the camera too much. So it's very asymmetric. I don't need a one-to-one relationship in my uplink and downlink. I really need something that can give me, if I've got a 450 megabit per second link, I need something that can give me a lot more in one direction than another. And the answer to that is what we call the PTP 700. And the PTP 700 has the ability to set up a number of different symmetries, or link symmetries, what we call them. And adaptive symmetry is by first the default on the radio, but it's also the most intriguing because it can actually change our time division duplex timing and go from 50-50 or one-to-one relationship up and down. And as data demand is generated by the associated equipment around it, we can actually shift our timing up to 90% in one direction, giving us a 9-to-1 configuration. Or in a 450 megabit link, I can get 400 megabits in one direction and still have 40 plus back in the other direction for, phone calls, voice over IP, camera control, pings of devices and keep alive and management and things like that. So it really, really gives us a lot of flexibility. We can still hard code things as well. So I can do one-to-one if that's required, and that's more of backbone configurations. I can go 1-2 or 2-1, 3-1, 5-1, etc. So we can set up specific hard-coded symmetry, or we can let the radio do it by itself. And vastly all of our customers in this space use the 9-to-1 or up to 9-to-1 as we go. And it's a very nice feature. It is a little bit tied to channel bandwidth. So when you get to a 5 megahertz, very, very small channel, you're not going to get 9-to-1. Really a little bit more restricted than what we can do per channel bandwidth, and we can certainly document that, and it is documented in the user's guides. But that's just a question of what's available to you, and this is where the PTP 700 really shines, is that we can use that single channel bandwidth, and we can actually deliver high throughput in one direction for our customers. So next slide, please. Okay, so what are some of the challenges that we face? Right? Well, there's topologies, point-to-point, point-to-multipoint, using rings for configurations. Those are all actually pretty cool concepts, because there's times when a point-to-point spur is a great asset to our network, but it's a spur, and either we have a lot of redundancy with it, or we want to double the hardware, things like that, and we might be able to actually do better both from a hardware and a resiliency standpoint if we did point-to-multipoint, or we did G.8032 rings, so something along those lines like that. Those are the things that allow us to add some flexibility to the network and some resiliency. So instead of having two pieces of hardware at a site to do a 1+1 hot standby, if I can do an east-west type configuration at all my sites where I've actually got two different paths off that same site, I'm less dependent and have a higher degree of redundancy. So those are some things. Of course, terrain can be very, very tough and very challenging. It can be very, very, rugged. You can have mountains that are within 1 mile of lateral distance. You might have a mountain that actually goes up straight up a mile and then straight down. So it literally looks like a big triangle. That's just a big chunk of rock that sticks up and blocks line of sight. Those are pretty tough because there's not, in lots of times, there's no place up there to co-locate anything, and there's no power, certainly. Those locations are tough. And also you wind up having where you've got very, very flat terrain and you've got to deal with earth curve. So how do I deal with earth curve? Well, that's with towers and expandable masts, things like that are going to give you shorter distances. And there's some other challenges there as well. So we'll talk about that. We'll talk about RF resiliency a little bit, frequency agility, and then frequency efficiency are the next things that we're going to talk about here. So next slide, please. All right. So one radio, many missions. That's a tagline that we've seen with PTP 700 for a while now. And why is that? Well, this picture kind of gives you gives you an idea. I can have high capacity multi-point, where I'm actually connecting wide angle sector antennas to multiple remote sites. I can have reflective non-line of sight, diffractive non-line of sight. I can have point-to-point serial configurations where I'm going from A to B to C to D. And then I can have high capacity backbones connecting back to whatever the network is going to be. And I can, of course, cross connect into the fiber if there's user fiber available, so I can be on the bigger network. So it gives you the option of having both obstructed paths, line of sight paths, as well as high capacity multi-point, all in the same radio, all with one set of software, one set of sparing, one set of training, one set of documents. Makes the operator's life a lot easier when you're not having to learn 9 different devices on your network at the same time. So next slide. And so if you think about it, we're pulling from the edge. If I'm in a network configuration where I've got a border, and then that border needs multiple remote sites on it, so I can have eyes on all the terrain. Maybe it's it's rolling hills, or it's very mountainous, or it's very, very flat, or I'm looking out over the ocean and I'm trying to monitor the coastline and the edge of the Earth curve and where that is. Well, we might use high capacity multi-point for that, where I'm aggregating back into the network with PTP 700. And I might have line of sight or non-line of sight configurations. And then from there, we might actually add on PTP 820. And there's 2 different configurations of 820. There's what we call a Charlie and a Golf. 820C or Charlie is an all-outdoor solution, multi-core radio. And then I've got 820 Golf, which allows a split mount design. So there's different configurations based on requirements. So Susie, next slide. Thank you. And then going from the core to the edge, or adding on to that, as I'm bringing all my data back into my network, and I'm getting it to where it's got to go, I might build myself an 820G network or an 820C network, and use a ring configuration to allow for high resiliency and high redundancy amongst all my dedicated assets, all the places where the network operating centers are. So you can see we lay it out in multiple places where I can use these radios in lots of different ways, both point to multi-point, depending on what the configuration is, what the terrain is, all the different challenges that we have there. The next slide. All right, so rugged terrain. So, the thing is that is interesting, of course, and we'll talk about LINKPlanner a little bit, and this is a screenshot right out of LINKPlanner, is that we have very rugged terrain. It can be very, very high. And you look at the left edge of that graph, and you can see that we go from, relatively high at around 6,000 feet or 2,200 meters, and within 90 kilometers, we're down at 1,000. And you've got some significant down tilt there, and you've got some significant thermal ducting as well. And so that you've got a dark brown shade. That's the actual hard terrain of the ground. That's the dirt. And then the light shaded area that's above it, that's your thermal ducting line. So you really got to make sure you keep in mind that you have to not just plan for the ground, you've got to plan for the thermal ducting, and we'll talk about that just a little bit as well. So next slide, please. All right, so this one's an interesting one as well. I did this configuration not too long ago, and we are trying to get, and I just want to bring up 2 things of note here. One is we're trying to get down along a coast, so we're trying to basically go from land tower to land tower without the assistance of any mountains or high terrain anywhere, trying to get over the water. And as you can see, it looks pretty much like that's straight up water. And that's at 30 miles or 40 something kilometers. And that's you can see that you've got good earth curve there, so you got to get pretty high at each end from a tower standpoint. But then you want to look at that. You can see the shaded area, that lead shaded area that represents the thermal ducting. That area there, you can see how much the earth bulge actually grows during the hottest times of the year. And this link, though the Fresnel zone without the thermal ducting included, would say that that's line of sight. That Fresnel zone is completely clear, but there's going to be times of the year where this link actually becomes non-line of sight because there's because the earth curve gets much worse based on thermal ducting effects. And so that's something that's really get planned in as well. We're going to talk about link planning in a little bit, but these terrain factors play into this. And this is where we go back and we say, okay, if a competitor in a competitive situation, I've got PTP 700, which is not the most inexpensive radio in the world, but what it is, it's a very good radio, and it comes with planning tools from Cambium networks that allow us to identify these things. And I love it when competitors say we can do it with this, and then I say no, you can't. You need this. You need Y instead of X, and because I know exactly what's happening because I've done everything in LINKPlanner, and they don't have tools like this. Makes us look really good, especially when in trial situations or when people go to deploy and they have a limited deployment because they've won the opportunity away from us, and then they fail, and then we get invited back in. So that always looks good for us. So next slide, please. And so fade mitigation. Right, so we just talked about thermal ducting. Thermal ducting is one of the various types of RF fading that we could talk about. And there's multipath, and there's dispersion. There's lots of different things that we could talk about. But we're gonna kind of just lump them all in and say, how do you mitigate fading? Right, fade mitigation standpoint. What are the technologies that you can use that will help with fade mitigation? And there's a number of things that are out in the industry. There's technologies that existed for a long time. One thing we've been doing and the PTP 700 radio for people that have background in with PTP 600 or earlier as well, may have heard me say over the years something called multi-beam space-time coding. It's another way of stating MIMO, or multiple input, multiple output. The 700 series radio has 2 transmitters and 2 receivers, and there's actually something in between them it's a maximum ratio combiner, and we call it a space-time decoder. It's a cute thing in the slide that kind of gives it a little magic air, but it really is the magic secret sauce of the radio, where it can actually decouple and decorrelate all of the distortion. And that happens from near and non-line of sight, and from when we've got significant multipath. Things like that. All those things can happen, and there's times you just go, there's no way this should work. But yeah, you put the radios up, and they do work, and they work really well. That's when you go, okay, this really is magic. But this multi-beam space-time coding is really awesome, and it's a maximum ratio combiner that really makes it happen. And that's not something you really see in the industry when it comes to people using Wi-Fi chipsets and things like that. That technology just isn't available, to the degree in a chipset that we can develop. So you can see that on the far right upper corner, you've got, any single carrier system could have a fade. Any radio signals can fade, whether it be thermal ducting or multipath, etc. And how long the fade is for is to what the result is. If it's a very fast fade and it's not very significant, you can make it up with some additional transmit power or dropping modulations, things like that. But if the fade has any length to it, your system could be down. With a MIMO system, or a space-time coded MIMO system, I've got multiple carriers that are going to be separate from each other, and I will actually be able to take the best of each one of those, maximum ratio combining the best of each one, and actually come up with something that may slow down but not go down. And what that really does is it actually helps with from a fade margin standpoint. So if I've got a 40 dB fade that I could be subject to, I can get away with less fade margin and smaller antennas and still be able to work and be working to some degree. So that's something that the product brings to bear. In addition to that, a variable OFDM structure I don't know of anybody else that does this in the world besides us. We call this intelligent OFDM, where we can actually not only pack in more subcarriers, therefore more spectrally efficient, but we can change that up, number of subcarriers based upon the actual geometry of the link. Because multipath, as you all I'm sure are aware, is really a geometry problem. It's based on frequency, and it's based on length of the path and reflective points. And so if I've got frequency specific fading because of the frequency I'm on, changing frequency or changing the path a little bit by lowering antennas and bringing antennas up and down, those are the kinds of things that actually change the geometry. Well, we can do the exact same thing without having to do any of that by changing the number of subcarriers. And each subcarrier has a different center frequency. And so we can actually change those by using the number of subcarriers involved and the bandwidth of each subcarrier. That allows us to overcome significant multipath. And of course, we also support polarization and space diversity at the same time. So I can have one antenna, dual polarity at one end, and two antennas at the other end of the link, one of each polarity, and avoid the multipath that you would get with a single polarity system. So next slide, please. Okay, so just to give you an idea, this is an example of something that this is a true photograph customer sent to me from in New England, it's a National Guard unit there. And right after Tropical Storm Irene had come through, had been Hurricane Irene at one point, but once it came through, this 12-mile link with 4-foot dishes, which was 300 megabits per second, and everything was working perfectly. After the storm, they realized the link was still up, and they were going, holy cow, but it's going really slow. They thought, well, it must be an antenna alignment problem. And you can see that based on the circle that shows where the target was, and then where the antenna is pointing now, it was a full 90 degrees off and 30 dB down in signal strength, but still had enough fade margin and maximum ratio combining to keep the link up. Now, it wasn't 300 megabits anymore, it was 6 megabits, but awfully more than zero. So, and I would say 6 megabits is infinitely more than zero. And of course, you can see where the tower aided in our installation by actually stopping the antenna from going any farther and putting a very nice dent in the antenna. So that's just one of the nice things that we've been able to see with this radio. So next slide, please. Spectrum. If I've got a challenging environment, especially in a border environment, if it's regulated between two countries, you don't generally see you don't see as much. So between the United States and Canada, for example, we would expect to use a fixed frequency because we know that it's a licensed frequency in both countries, has been coordinated, and we don't have as much trouble there as we might. But if we're in some other places where maybe it's unregulated and we don't have quite the licensing functions, we can find where we have self-jamming as well as intentional jamming and just plain old interference. All those things can be true depending on what's available in a particular country or at a particular border. All of those are important. And so we've got a dynamic spectrum optimization. We've got a full-time spectrum analyzer that's built into the device. So you get the actual spectrum at both ends of the link. We actually see what's going on. We can actually be proactive and move to a better channel if one exists. We can be reactive and move away from interference if interference comes up. We can actually give you 25 hours of history on each channel. So we're actually tracking along as we go. And then we can actually be both TDD and FDD. So what I mean by that is that I can be both single frequency for send and receive at both locations, or I can be frequency division duplex, where I can actually have a different frequency for send and a different frequency for receiving. And that really ties into what's called asymmetric DFS or asymmetric DSO. And if you think about it, that Susie, who's my partner in this webinar, at her end of a link, channel 1 is her best frequency to receive on. Well, I could send to her on channel 1, but at my end of the link, channel 48 is the best one to receive on. She could send to me on channel 48. So we could actually be split frequency, and that gives us significant amount of frequency availability. If you think about it on the PTP 45700, where it has it has better than 1.5 gigahertz of addressable spectrum, and using a small 5 megahertz channel, I have around 285 channel possibilities at each end. And if I'm on channel 1 and Susie's on channel 1, that's one possibility. I'm on channel 1, she's receiving on channel 2, that's 2 possibilities. She goes to channel 3, that's 3 possibilities. All right, so we can work that up. If you actually do the math on it, it's 285 times 285. It's nearly 90,000 unique channel combinations that can exist between the two ends of us. It gives us an awful lot of places to hide when there's jamming and interference to make the link work that nothing else might be able to if you are bound to a single channel at both ends. So basically, at the end of the day, this gives us complete frequency control and allows us to do exactly what we need to make the system work. So next slide, please. All right, so just a graphic of this always-on spectrum analyzer, and gives you the ability to look and see not only from the top portion of the graph, which is actually what's going on across the spectrum, but also gives you a history of that spectrum as well. That's the bottom graph. The bottom graph can go for 25 hours. So I can be looking at the nice light shaded blue is really good. The medium blues are not so good. The oranges are, the light oranges are not good at all. And the really dark oranges are high interference areas. So this gives me, if I'm thinking about it and I've got spectrum management to work with, and they're saying you need to operate on channel X and channel Y, if I set up there and then I see them being interfered with, I'm able to pull this data and send it back to those spectrum managers, be able to say, I need some spectrum help. So this allows for significant co-location, both of devices, whether it be mine and others, and the ability to track down jamming as well. So next slide. Okay, so this one, and Susie's got to keep hitting enter a couple times here. Basically, what this says is that we've got a superheterodyne receiver in the PTP 700, and what that allows for is that's both static filtering and dynamic filtering. And you can keep hitting a couple more times. Okay, and basically, what happens is that we're able to actually be able to sneak into places where there's a clean channel. We can actually lock in on that clean channel and then bring in the both the hard filters existing, the bandpass filters, as well as the soft filters, and bring them down around the channel that we want to talk on. And I think you hit one or two more times here. One more time. There you go. And so we can actually, if we change channels, that dynamic filtering goes with us as well. So the superheterodyne receiver and the dynamic filtering really allows us to have really good co-location, and also when there's high interference or high jamming issues going on, that we can avoid and still be able to operate as fast as we can possibly go. So next one. There you go. So let's talk a little bit about frequency division duplex versus time division duplex. Just to make sure everybody's clear on what this means. If I've got a FDD only system, that means I have a downlink channel and an uplink channel. So I've got a transmitter going left, I've got a transmitter going right, and associated receivers with them. You have no frequency agility generally, except on the PTP 700, which can be agile at the same time. Whereas in a time division duplex, using the same channel for up and down, time division duplex will not give you the same capacity as a fixed or frequency division duplex channel will, because you're not time sharing between the ups and the downs. But it does give you significantly better spectrum usage. So it's really a question of what am I trying to accomplish at the time. Is to say which one do you really want to go with, and can I accomplish my goal from a throughput standpoint and a frequency usage standpoint. So PTP 700 does give us the availability to do both of these to some degree. So next slide. And I did talk about it earlier, the asymmetry. But if you think about here, if I've got a channel assignment at 20 megahertz up and 20 megahertz down, I can get 120 megabits, for example, at 6 bits per hertz in a full duplex environment. that might be great. But if I only need 80 megabits in one direction based on my high def cameras, with a time division duplex radio, I could actually do that with one 10 megahertz assignment versus two channels at 20 megahertz each. So the overall standpoint, because I'm actually able to use the asymmetric throughput that a PTP 700 gives me, it also allows me to use much less spectrum. And in places where spectrum can be tight, this is gold. By reducing my spectrum usage by 3/4 or 75% is really a significant gain, and really can have significant payback for all of us. Next slide, please. All right, so we're going to talk about network design just a little bit and link planning next. Because we really kind of talked about what our challenges were, how we solve some of those challenges, things like that. Now let's talk about just planning the network out a little bit. So if you could just go next. Okay, so co-location concepts. Both these pictures I took, and when you stack radios really closely together, it is not about it's not as easy as it might look. You go, holy cow, how am I going to make all this work? And we've got to deal with things like channel planning. We've got to deal with things like transfer power. If I've got a link that's 10 miles and one that's 1 mile, I need maximum power on that long link. I need a radio that can really power down on the other link. So having good automatic transfer power control and a really good range of power is also really important as well. And just so you know, the PTP 700 today can power down to minus 15 dBm, and it can go as high as plus 28 dBm. So it gives a really good range in 1 dB steps. So it gives me really, really good range when it comes to power, or if I've got to go very long distances, I've got the power. And if I got to go really short distances across the street, across a parking lot between two buildings, I'm not overpowering the environment either. So all those are true. And we can talk more about some of these things, but the co-location, there's lots of things. We talk about physical separation, angular separation, using obstructions to your advantage. We have a product called PTP Sync that allows us to synchronize multiple radios together that can add some significant improvement when it comes to co-location, density, etc. So next slide, please. Okay, so you think about co-location interference. If I had 4 locations and I had spurs off of each one of those, you know, I could see where there's lots of places where one link would interfere with another link, especially if it's nice and flat. And you don't have a lot of, especially if you don't have a lot of obstructions from trees or ground or earth curve or anything like that. If things are very, very tight, you could see a lot of co-location interference, in which case something like this, we might use PTP Sync, we might use high capacity multipoint, we might use a combination of those. All those things might play in there. So next slide, please. So some of you may be familiar with LINKPlanner, some of you may not. It is free. It is provided on our website. You do need a login on the support site. So if you haven't done so, it's not very hard at all. And it takes just a few minutes to be able to say, I need to register, provide some information, and then you have access to LINKPlanner. LINKPlanner can give you an offline map view. It can use Google Maps. There is Google Earth, where you can zoom in on links, things like that, so I can actually see what's going on for a particular location. All those are true. I can create sites, I can create links, and I can design networks completely with a LINKPlanner, and they can get as easy as 1 link or 2 links, and as complex as having hundreds in the same network at the same time. And I've been able to use LINKPlanner for all those examples. So next slide, please. Yeah, so the train download, train data worldwide is included. It's depending on where you are in the world as to the granularity of that data, but it's generally really pretty accurate. I normally use Google Earth as my other source to verify things, and I find that our data is really, really close to theirs, and they've got very fine data as well. So you can get train data, and once you get the train data and you've put in some points and you've created a link, and you've done your configuration at each end for frequency and bandwidth and antennas and antenna heights and things like that. Put in obstructions. All those things can be done here, where we can add in trees and buildings. to see what the effects are. You get some very, very nice outputs as well. So I get estimated signal strength, I get estimated throughput, I get estimated reliability, and I can actually add in what my minimum requirements are, and then I'll get a calculation that says this is what my availability is for that specific requirement. So next one, please. And then, of course, using Google Earth along with this, you can launch Google Earth right from LINKPlanner, and then from there you can actually zoom in. We lay out, as if you can see on the photo, the background photo, you can actually see the path has been laid out, and we increment it. So this one's being incremented 1 kilometer at a time, and then I can actually zoom in, and it'll actually be labeled down to 1/10 of a kilometer, or 100 meters, obviously, 100 something yards. And then from there, you can actually use the local photos that are built in and actually look at the actual, what are you really going over? In this particular case, you can see that I'm, from very, very high view, you really can't see that there's buildings, but once you zoom in on things, you see those buildings are all somewhere in the range of, 6 and 7 stories, 8 stories tall. And 8 stories tall, you're getting to about 100 feet, 30 meters or so. And now I've got obstructions that I've got to plan for. Those definitely play into my path. And if anyone hasn't noticed yet, in the small inset photo, very, very top left, it looks like somebody's standing on the roof. I think that's Batman. I think that's who it is. So you see, it looks like it. So anyway, so next one, please. So, and just kind of wrap up LINKPlanner. LINKPlanner gives you some really, really nice outputs. If you haven't used it yet, I urge you to try it. It's an excellent, excellent tool, and it will give you verified performance, and it will give you service level agreement, basically. So you can actually take this graph to your customers and say, this is what we expect this link to do. And I can tell you from thousands and thousands and thousands of paths that I've used over the years with LINKPlanner, good data in really provides great data out. And if your inputs are accurate, the LINKPlanner output will also be accurate. And you will find that we will not only perform, but in fact probably usually outperform what LINKPlanner says. So that makes for happy customers, and we all like those. There's also, and I'm not sure if I got a slide here on this, but just so you know, there's also proposal and installation reports that come both by the link and by the project. So that we've got things that we can send to our customers, we can send to the installation teams, we can add customized fields and do lots of very, very intricate detail with LINKPlanner as well. So it's a very, very nice tool all around, and definitely something you should try to, if you haven't used yet, you should definitely try. So next slide, please. Okay, so what are the issues with security? So we talked about, what requirements we have from capacity and from ruggedness of the device and reliability and some features that would be useful to have, in these, harder to reach areas sometimes. As well as urban environments. And then, but there's also the security aspect. I've got to have both secure communications over the air, and I also want to have, what about the devices themselves? So I got to think about intentional jamming, right? Does DSO help me there? Physical access to the devices. I mean, do we have tamper-evident tape on the devices so that we know that someone opened it or not? I mean, are they able to open it, or are the holes in it that I might be able to probe inside the device? What about the device security? What about over-the-air encryption and quality of service? Things like that. Do I have things where I can have separate VLANs and VLANs for management? And can I have things like that? And then, of course, denial of service attacks. What about over-the-air denial of service attacks? That's really jamming, of course. And then physical connections. If someone can get on my network, can they plug into my device, and can they overrun the network? And will the radio network or the microwave network, will it pass all of the traffic that's being generated to jam the network up internally, or is there some function to be able to stop that? And lastly, you got to think about the human aspects of security, and by far the biggest holes in any security system are the people. It's always the person that's really the hole in most cases. So roles and responsibilities are really important. What can and should be people doing or not doing? How do we regulate that? So next slide, please. Right. So the answer for most cases here, and it's something that we use is it's called FIPS 140-2. So FIPS 140 is a standard upon which cryptographic information is judged. It's not type 1 encryption, but it does cover. It gives us an overall baseline upon which we know that we have a minimum security level that is set, and it covers things like the cryptographic module itself, the actual ports and interfaces, what's open, what's not, roles, responsibility, authentication, physical security, environmental operational security, cryptographic key management, the keys that you're using to encrypt stored in the clear in the radio. So if someone stole your radio, they could then take out your keys somehow. Those are things that are important. Self-test diagnostics. Do we design properly and ensure that when the coding of the software is done, that it's stored in such a way that it can't easily be pirated away from us? And mitigations of other attacks like denial of service across Ethernet ports, etc. So all those are important, and FIPS 140 really covers all of those. So next one, please. So how do we solve some of this? Right? How do we solve these challenges? Well, PTP 700 is FIPS 140 validated, and that is the term we use. We don't say FIPS 140 certified or compliant. Those really don't. They mean that you're not validated. It means you haven't done a full job yet. Anyone can say, I'm compliant. I do everything FIPS 140 does. But if they knew that, then they would have actually just spent the extra few dollars and actually had the actual testing done. The testing itself it's expensive. Yet FIPS 140 validated for the first time, the entrance fee is around $150,000 to the testing laboratory before they'll submit to NIST for you to be FIPS 140 validated. That may seem like a lot of money, but the actual design work could be much, much higher. Your design engineers could spend much more money on the amount of time they put into on a project like this. So you might spend $1 million in development to get your product ready for FIPS 140 and $150,000 test. So if I say I'm compliant, that means you did all the work, but you just didn't get the test done. It's kind of like going 4 years of college to get a university degree and then actually not going to graduation and not picking up your diploma and having nothing to show for it. So it's obviously for us, it's a very important thing. The U.S. federal government requires validation, not compliance, not certified, because those terms effectively don't mean anything. Just keep that in mind. It is the PTP 700 is both a traditional microwave system as well as a tactical microwave system. You get frequency protection because it generally is licensed. We can operate in 4 and 5 gigahertz, or soon we'll be operating in 7 and 8 gigahertz as well. AES 56 with 0 overhead is very, very cool. TLS rekeying, it's another way of saying over-the-air rekeying, or OTAR. OTAR concepts have been around for a long time. We are the only company that I know that is currently deploying seamless over-the-air rekeying, where there is no downtime, there's no drop in network, there's no drop in data traffic as we rekey the AES encryption. And we do it without passing the AES key over the air. It's actually done using TLS algorithms, and that allows us to have a very, very secure over-the-air connection. Of course, the device itself is protected by HTTP/TLS. We have support radius, we have syslog for tracking, SNMPv3, IPv6, of course, or dual stack 4 and 6. Secure time server, in or out of band network management, login banners, unsuccessful attempts tracking, access control lists, and there's a number of other things as well that all go into that, that are all solved or all connected via PTP 700. So next one, please. Okay, and FIPS 140, the one thing it also does is it forces closure. Right? Anyone can say I do all these things. FIPS 140 software requires and actually forces all the closures. So I close insecure interfaces, such as extra Ethernet ports that aren't being used. They get turned off. Insecure ports Telnet, for example, gets turned off, and HTTP gets turned off. So those ports, port 80 and etc., those get turned off. So we don't even listen on those ports anymore. If you did a security scan with a FIPS 140 system, with our FIPS 140 system, you would only find port 443, which is HTTPS. That's the only thing you'll find. So, and we've been through many government scans over the years, and always pass because we can close everything. Minimum cryptographic key links, HTTPS, having the proper thumbprints for your certificates and keys, the right signatures on your software and your license keys, all those are required, and something, of course, we all do. And then you have complex usernames and passwords, and you can have significant amount of complexity there. I believe up to 31 characters on your passwords, which everyone loves to have a 31-character password, of course. So you get a minimum length, duration set for some changes, and you have roles and responsibilities that say I can have read-only users, I can admin users, and I can have super user or security users. All those can be assigned based on what's required. And then a login banners and confirmations, and then of course everything gets tracked via syslog. And I can have local syslog that'll give me the last rolling 2,000 entries, or I can have syslog messages sent to a syslog server on my network. So anytime anyone logs in from the IP address that they're logging in from, who it is, when they did it, any changes that were made, we can track all of that down to the person. So it's something that's important. And of course, the big yellow triangle is because that's a warning symbol, and people make mistakes. So that's why we have these things and these policies. Makes things a lot easier for us. And so next slide, please. Okay, and so if you log into a PTP 700, for example, you might see FIPS 140 validated, and you see a big yellow triangle. And if you click on the alarm page, it'll say, what's wrong? And the alarms will show things like the secure mode's not configured. You can have FIPS 140 validated license key, allowing the feature to work. You can have the software loaded, allowing the feature to work and be configured. But until you actually close all the security, you're going to get the alarm. So it's something that we like, that shows that we are not only compliant and validated, but configured. So next slide, please. All right, so over-the-air methods, both 700 and 820 series radios have 0 overhead. So we're going to give you the same throughput at the Ethernet port, whether you've got AES turned on or not. Right, so we built all that, and it's a purpose-built system. Right, so, and we don't care what kind of traffic you're sending across, what kind of patterns, what kind of sizes, frames, etc. We do it all, and we also have the option for both an RSA-based, TLS published certificate-based AES 256 encryption, which we can have seamless rekeying every 60 minutes. Right? You can use a factory embedded, or if you're using FIPS 140 software, it's a user-generated certificate has to be done, or you can use a pre-shared symmetric 56-bit AES key. And it's got to be the same at both ends. That is part of authentication at that point as well. And lastly, you can also still use that for those symmetric keys that then become the seed keys for TLS rekeying as well, up to every 60 minutes. And so, with that said, everything's FIPS 197 validated, okay? And as I think I mentioned, on the 700, the AES encryption has to match, and that's part of authentication as well. Otherwise, the link won't come up. And of course, it requires an AES license. All of our features require license keys, but that's fine. Okay, so I think next slide here. I think just to wrap things up, not sure if we have any questions yet, but if we do, be happy to answer. And I think we kind of covered all of what are the requirements, what are the kinds of components that are required, what are some of the features that will help you solve some of these border security challenges, and then lastly, how we can make it secure.
Okay, thanks, Bob. We have one question. Is the factory temperature test will be for each single piece of PTP 700?
Okay, that's a very good question. So yes, the answer is that every single PTP 700 outdoor unit, or ODU, every last one of them goes through that complete temperature testing every time. No, none of them, not a single ODU leaves the factory ever without passing that test.
Great. And the only other thing I see here in our questions box is a hello from ATL.
Cool.
And we can wait another minute to see if we get any more questions, but thank you everybody again for being patient with us during our technical difficulties this morning. This webinar will be posted to community and our YouTube page after we conclude here. And I don't see any more questions. Bob, do you have anything else for our audience?
Yeah, I'd like to just say thank you again for listening to me for the entire time. Sorry for the lateness of what we did, but hopefully it was of some value. If you have any questions, certainly we as especially anything that has to do with the any defense and security space, both around the world as well as in the United States or Canada, that is all covered by my team, and we can be reached at fedsales@cambiumnetworks.com or through normal marketing channels as well. And we'd be more than happy to help anyone as they need it.
Okay, thank you, Bob. We're getting a few more questions. Yes, this will be posted in PDF format on the community. Hello from Indonesia. Thank you from Alaska. And it looks like that is it.
Okay. Well, thank you for the comments again. And if anyone has anything you'd like to talk about, please let us know.
All right. Thanks, Bob. Thank you, everybody.
Thank you.
Have a great day.
Thank you, Susie. Thank you, Susie. Bye-bye.
Bye.